Okay, so I already chit-chatted with you. So I'm Santosh. Bangalore is my home. Like I grew up in Bangalore. My parents live in Bangalore, so I visit home. And I've been living in the US for like 15, 17 years now. I'm a professor there. But more importantly, like why do you give talks, right? To teach people, to educate. And educate, like knowing the name of something. Just Richard Feynman said it, right? Like knowing the name of something is useless. You know something when you understand it deeply. So one thing I want you to take away is not a lot of jargon. Like, no, you're not even my name, but to understand like at least 3 ideas core to your heart, so that you can convey this idea to anyone else in your community. That's how you grow knowledge. And to do this, I need your assistance. If you all just are a silent audience, I can't gauge where your heart is or where your head is. So I want participation. Okay, so if you don't understand something, I don't have to cover all the slides, right? You should pause and ask, I don't understand. Can you, if you can highlight what is the aspect that you don't understand. Okay, and thanks for coming on a Saturday afternoon. Weekends are precious. Okay, so I'm going to, there is correctly rounded math libraries, AI, and various other things. Okay, so let me start out by saying, how important is plumbing in your house? We are not in the Stone Ages, right? Like plumbing is very important. If you don't have plumbing, you don't have water, right? And your sewer systems will not work. Okay, so it's very important. And what are the key things in computing that are important for your computing systems to work? Sometimes we take it for granted. I want some inputs.
Hardware.
Hardware, yes. What in hardware?
RAM, storage.
Okay, yeah. Like, what is the key component of anything that when you want to represent it?
Bits and bytes. Input device.
Bits and bytes. Okay. Even the Romans designed numbers. And what is your fancy ASCII or fancy languages? They're all zeros and ones. So you need a way to represent zeros and ones. Okay. So that's what like numerics is the way to think about. So if you understand numerics, you understand everything. Everything else is just encoding. If you understand ASCII, you can encode any language, right? So everything A is 65, and so on. So everything is just numbers. So the one message I want you to take away is numerics are the plumbing of your computing system. And we are realizing with machine learning, like every vendor is like releasing their custom representation. And it's dictated by what is happening in the field. You want to run large parameter models to get more accuracy. Okay, so to get the thing started, I'm going to give you a very simple C code. How many of you have written some program in C? Okay, most of you in India, right? Like in the US, people start with OCaml or like Elixir or whatever their favorite language is. If I show this code, like I don't know what the C code is. Okay, at least like if it's I'm teaching a freshman class, right? Okay, this is a very simple program. I will walk you through. Don't worry. Like if you have a data type, I am using a data type called float. What is float? You want to represent fractions and real numbers. Like float is a 32-bit version of it. So I have an increment. What is my increment? 0.1f. It's a 0.1 in floating in 32-bit float. That's what a f stands for. And I'm accumulating. Rest is equal to 0.f. Here, what I'm going to do is in the loop, I'm accumulating increment 10,000 times. 10,000 times, yes, right. So I'm adding 0.1 10,000 times. Okay. All of us have done high school math, right? According to our high school grades, what should this be? 1,000. And what do I have? The result is not 1,000 about this program. Okay, everyone with me, right? Everyone understands this program. If I run this program, how many of you say this program will abort? Will not abort? I don't know what it happens. Let's start. How many of you will think it will abort? Raise your hand. Okay, about 50%. How many of you think this will work as is? Like just exit. No one thinks it will exit. What will it do otherwise?
It will be a 0.0 something. won't be equal to that number.
Yeah, right. Okay, but if it's not equal, it should abort, right?
Comparing floats with integers.
So very good. You are compilers people, right? What happens when you have a comparison like this?
Static cast.
There is a static cast happening.
Yeah.
So one way the compilers would do, it would promote, because there's a floating point type here and you're comparing it. There are two ways to go about it. You can static cast demote rest to an integer and then compare. Or you could promote 1000 in integer to a float and then compare. So there is an implicit cast happening. Okay, we are very good. In most compilers, you take your Clang compiler, or Clang is LLVM, right? Or like GCC, this would abort. So can someone tell me why this would abort? So it's aborting because res is not equal to 1000. Okay, why is res not equal to 1000?
Floating point inaccuracy.
Okay, floating point inaccuracy. What is inaccurate here?
So take a 0.1, it doesn't have an exact binary representation.
Awesome. So 0.1 is easily representable in decimal. But when you convert 0.1 to binary 32-bit floating point, it's not exactly representable. You need to round it. Like you go to a restaurant, the bill is my Uber driver's bill was 449 rupees, 32 paise, right? So I said like, oh, I don't have paisas anymore. I just have 433 rupees. So you round it. So as you figured out, 0.1 is not exactly representable in binary floating point. And what happens is there is a rounding that is happening, which is done by your runtime. As a result, like, the actual answer is something like 999.9 or something, and which is not equal to 1000, because 1000 is promoted to floating point and then it's being compared. Most compilers it would abort. Okay, so you're writing like this code is a common part of like most scientific computing applications. How many of you have written a gradient descent algorithm? Okay, so if you're doing machine learning, the first thing you need to learn is how to do backpropagation, right? You do some gradient descent algorithms. This is a nugget of whatever you do in gradient descent. You have an increment, you have a time step, you keep iterating, and you have an increment something like this. So you have to be you have to be careful in choosing the parameter. Okay. So the moral of the story is seemingly innocuous code got you wondering about things, right? So now I'm going to talk about math libraries. So you don't wake up one day and start doing math libraries. I'm going to tell you a story about how my group started exploring math libraries. Long time ago, I used to work on compiler verification. You can see my LLVM dev talk in 2012, talking to LLVM developers and saying we have formalized the semantics of the LLVM IR. One of the cool things in the LLVM space is it's a mid-level IR. The higher HIR is pretty nice. It has a two-entity system with pointer types and non-pointer types, and cas happen explicitly. It's kind of elegant. And for me, when I was a PhD student, like about 17 years ago, I could write a PLDI paper. PLDI is a premier conference in compilers and language design. And I had an idea about enforcing memory safety, and I could translate it in like about 6 months. From an idea to a working prototype that will work with real life code. And LLVM was a key enabler. Okay. So, and we understood, like we knew a lot about LLVM IR, and like we understood the semantic, we tried to tease out the semantics. What does semantics mean? What does each instruction actually mean mathematically? And why is this important? So LLVM is a compiler for C and C++, right? And C and C++ expects every professional writing code in it to be an expert programmer who doesn't make mistakes. And if you have a mistake, your program is considered to have undefined behavior. And the language says, if your program has undefined behavior, the language standard says, it can do whatever. The compiler is free to do whatever it wants. Even set your house on fire. Okay, so the compiler operates with assumption. This is a code written by an expert, and you have undefined behavior. That means no sane programmer would have written it. Okay, so it should be dead code. It will just optimize everything away. And now you want to enable aggressive optimizations. That's one of the reasons how you get performance on modern systems, right? So as a compiler developer, you follow the rule of the law. If your rule of the law allows you to go both sides of the road, you will go both sides of the road, right? For a compiler developer, the rule of the law is the language standard, okay? Or whatever GCC does. That's what most people do now. So you have to understand how to actually optimize. So we formalized it, and LLVM was trying to encode the various kinds of undefined behavior a compiler can exhibit. Like even now, there is poison values, undef values, and the semantics are kind of a mess. So we started teasing it out, and that was my talk in LLVM Dev. Okay, and then when I started my as a professor in 2012, I wanted my students to do something, and so then we said, what is the most buggiest piece in LLVM? And it turned out people optimizers tend to be very buggy. Why? Like there's a pattern that you want to optimize, and it turns out like it's useful in your setting. But if you don't precondition the inputs or carefully think about all other scenarios, you will have invalid transformations in other settings. And John Reger had found like a C-Smith tool, and he had discovered a lot of bugs in LLVM and many other mainstream compilers. So we set out, let's keep our ambition low. We designed a domain-specific language to express people optimizations in LLVM. Okay. So our goal was that the LLVM developer would specify the optimization in our language. Our runtime or interpreter would generate SMT solvers. These are satisfiability modulo theory solvers. These are like theorem provers, automated theorem provers. They would generate mathematical formula for them. If the theorem prover says yes, it's valid, then you would generate C++ code. Okay. Now, 12 years hence, after we started this project, now if you want to add a new optimization to LLVM, it's checked through Alive. It's our all automatic LLVM instruction combined verifier. It's in collaboration with Nuno Lopez, my student David Menendez, and John Reger. And Nuno, who's an LLVM developer, took it further by actually putting in a lot of effort to make it like usable by mainstream developers. So we wrote a lot of papers, and we got like my student won the best dissertation award and various other things. And during this point, we primarily focused on integers. And if you talk to LLVM developers, they don't even want to touch floating, precisely for the reason we just saw. Right, 0.1 is not representable. Like there are a lot of snafus. Okay, they don't even want to touch floating. And when we built an extension of Alive, we called it Alive FP. Floating point optimizations were on. And how many of you know how many zeros are there in floating point? There are two zeros, -0 and +0. And there was an optimization in LLVM which was changing the sign of 0. And I remember my student saying, Santosh, I found a bug, like it changes the sign of 0. And my another student saying, who cares about 0, sign of zeros? And then my student, like, he's well versed in this topic. He said, oh, you should read William Kahn's article. If you change the sign of 0, it's going to introduce discontinuities in branch cuts. And for people who don't know William Kahn, he's a Turing Award winner. It's a Nobel Prize of Computing, right? He was the person responsible building the community to get the IEEE 754 standard. Earlier, everyone, like what is happening in the machine learning age now, right? Everyone is designing 8-bit, 9-bit, 3-bit, 4-bit floating point representation. How do you interoperate between across ecosystems? It's a nightmare. Okay, so IEEE, it's not a new thing. It happened in the past. Before 1985, people would build their own custom representations, and your code wouldn't interoperate. Libraries wouldn't interoperate. So William Kahn put in a lot of effort to get the standards committee to standardize floating point. That enabled portability. So he had a nice article. So we reported this bug. Within hours, LLVM developers fixed it. Okay. And then there is this demonic mode in any compiler called fastmap. Okay, so so everyone knows, like, do people know what associativity is?
A plus B equals B.
You have three numbers, right? A, B, and C. Let's say you have an addition operator, A plus B plus C. You can do A plus B first and then add C. That's your LHS. Your RHS is you add B plus C and then add A. Okay, this is associativity. It's a powerful law, like we learn in like 4th grade or 5th grade. I don't recall when, but like it's a key element of mathematics, right? But floating point arithmetic is not associative because of rounding errors. Okay, and if you want to do, this is where in NVIDIA premises, if you want to do parallel computing, you need associativity. Without parallel computing, your preface scan or any of your parallel algorithms wouldn't work. Your SIMD optimizations wouldn't work. Your vectorization doesn't work. You need associativity. Okay, floating point is not associative. Now, as a compiler developer, what do? You can think like I can't optimize, but that means like decades worth of parallelism is all down the drain. So the compiler developers found a nice mode where you try to overlook some of the aspects. So this is what fast math is. Fast math treats any real number identity as a floating point identity and then optimizes your code. So in reality, it's like the other person is like driving on the wrong side of the road. You don't say, yeah, you just overlook it and go past. Close your eyes and go the other side, right? So almost all compilers have it. It's needed for vectorization. And it can cause total foobar errors. Okay. So what happened with us? My student took a machine learning course, Age of Machine Learning, right? And we also need our PhD students to be experts in multiple. You need to have breadth in computer science, not just depth in your area, right? He was supposed to design a support vector machine algorithm. Now it's very dated. Like 15 years ago, you did an SVM classifier, we will be jumping with joy. But now you just need to build transformers, right?
Just one question, Professor. When you mean you treat integer identities as floating point identities or real identities, right?
Real number identities. So yeah, well, some of them integers are associated. Yeah. So, but floating point numbers are not associated. You had a question, right?
So, Professor, the optimizations, as you said, are in modes. So there is a GNU C++ standard based mode where they don't do all these things. You have to explicitly specify it when you're compiling stuff.
So if you do MAVX or if you do mark equal to native, which is the general mode, like whatever all the native optimizations enabled by your machine, they all use it. Even if you do -C standard C11, 17, C17 or C21, they still do it because this is totally different from the C standard. C standard does not say anything about like floating point optimization. This is a different standard.
Like, why should we even have fast math in the first place? Because if someone is going to use fast math, then they must know that they are going to use certain fractions, which will allow associativity or these vectorized operations on them. But if
I understand your question. So now you have your GPU. Can you just use one lane on your GPU when your GPU has like 1024 streaming processors? So to do that, your code has to be vectorized. Otherwise, you are not utilizing all the resources on your GPU. Utilization, performance. So like if your cat face is not recognized in like microseconds, you would not even like look at it, right? So you want speed. Performance matters. So it's primarily for performance.
And can we not have like operations which allow for some tolerance, like whenever we are doing a comparison or whenever we are doing any operation?
You as an application developer has to do it.
Something like a tnum struct, instead of using a 32-bit or 64 bits floating point, we always use tnums for stuff like this. That we can say that we are not sure about these bits. These we have some like.
Yeah, so I think like you're confusing two things. One is there is tnums is like just adding like some sort of uncertainty, but that is not what like modern like you have a regular C program, as I said, like what I showed like just like in the previous slide, and you want to compile it. You are a compiler engineer, and you want to get the best possible performance. You as as a programmer, I can do a lot of cool things. I can use interval arithmetic to bound bounds. I can do a lot of other things. I can do a lot of reasoning. But you have code written by people. You need to compile it. And what is the rule of the law? The standard. Compile according to the standard. Okay. So fast math is important. Moral of the story is like today you get performance. Your laptop has GPU. It exploits performance because of fast math. But in reality, if you don't compile your code with fast math, you're going to be very slow. None of the almost 2 decades of work, efforts of 2 decades worth of work is not being used. So people use fast math all the time. Even when you just run O2, it calls fast math. Okay. So coming back to my student story, he took a support vector machine. He was implementing a support vector machine algorithm, and it turned out his deadline was around. His training time was like about 8 hours, and he made a fix to the algorithm. He wanted to do it quickly. He enabled fast math. The accuracy of the algorithm tanked from about 80% to 30%. Same data set, same number of iterations. All he did was change the compiler flags from use fast math. Okay, the accuracy can tank. Now you are a machine learning engineer. You're deploying models, and all you did is change like some parameters of your compilation flags, and your accuracy can tank. Now, good luck debugging it. Right? So we had the same issue. And fortunately, I'm a professor. I have students who come in, and like I told this problem to my student, and the student who was working on LLVM compiler said, "I'm sick of you." He graduated. He found a real job and wanted to make real money. My other student was the guinea pig, and Sangeeta Chowdhury, she's at AMD Research. She built a shadow execution engine. So now you have an algorithm which is producing weird result with fast math without fast math. What is happening? Where is the error happening? So what did we do? So let's simulate real numbers. That's infinite precision. There's a library for doing it. It's called MPFR. We took the program, replaced every float type with MPFR type, and then we would have the regular program, and we would do lockstep comparison of the results. And the first place where the errors would happen is in a call to math library. What is a math library? You have e power x, sin x, cos x, ln of x. Okay. And then we wanted to investigate why is it this happening? And this is what my other PhD students started working on. Okay. So the moral of the story is math libraries, like whatever your GCC, GNUs, math libraries, they're all wrong to a certain degree. Okay. So now you may be asking, what is correctness for math libraries, right?
GPS signal lost.
Okay. So they're wrong with some alps, like 1, 2 KLs. Okay. So we wanted to then in our about 6 years ago, we set out, okay, if people have not built correctly rounded math libraries, let's try building. Let's understand why are people not building it. Okay. This is how this project started. Okay, to summarize the context, floating point numerics are very important, and compilers have to honor whatever the standards say in the numerics. Portability is very important. Like if all you do is just run on NVIDIA GPUs, you can just trust NVIDIA guys to do a good thing, right? But you want it. Diversity is part of life, right? You'll have a system. The cluster will have some AMD GPUs, some Intel GPUs, or some NVIDIA GPUs. Now you don't want to be rewriting everything for different frameworks all the time, right? So you want portability, and this is what standards and reproducibility, correct rounding will help you. So someone had a question.
Okay. Professor, quick question on the machine learning part.
Mm-hmm.
So most machine learning pipelines won't compile code. Rather, they'll write it in high-level language, which is interpreted. The kernel is actually compiled, written in C++. So with an error, it's consistent across PyTorch, unless and until you're shifting from TPUs to CUDA.
Mm-hmm.
So either we are not aware of this, which I think is the case, or probably the model architecture itself is fault tolerant enough.
Okay, so yeah, Santosh is this programming languages guy, right? Like he's just preaching to the choir, saying important. Okay, so Ali Rahimi, he is a machine learning researcher. If you don't know, he's a very well-known researcher. He won the Test of Time Award in NeurIPS. NeurIPS is a machine learning conference for people who don't know. People present their interesting machine learning work there. So when you win Test of Time Awards, you give like a retrospective lecture. Okay, and then Ali Rahimi was describing his experience. He was in a particular company. I want to take the name. And in that company, he was training multi-billion parameter models with TensorFlow. Okay, and his team member noticed that round to zero truncation is very effective in hardware. So he changed the rounding mode of a production system to round to zero on the TensorFlow. The accuracy of the model tanked to 20%. Like this is what Ali Rahimi says, 17 minutes in his talk. Just search for Ali Rahimi NeurIPS Test of Time talk and listen to it. It's like 25 minutes talk. Beautiful. Okay. And he says that just changing the rounding mode and pages were beeping for a lot of people. Okay. And it took time and the accuracy tanked literally. So the moral of the story is the entire machine learning ecosystem. We have built a very cool ecosystem with like 2 pods as the foundation, like 2 chairs as the foundation, right? And you have tons of weight on these wooden logs that needs to be that's holding the weight of the entire ecosystem. When will it get crushed, or will we find reinforcement very quickly so that we can make cool things? That is the message I want you to take away from this talk.
Actually, now it has started because people have started to program on a lower language like Triton or LLVM, where the actual matrix multiplications are being written.
Yeah, so NumPy is pretty great. Like there are like various customized ports for it. But again, to reason about abstractions, like people are experiencing, people who build like these low-level libraries, they are facing this. And if you are in a big company, you get these issues all the time. Just look at the PyTorch mailing list, or just follow Ed Zhang. Like he's the chief developer of PyTorch 2. Like, and he posts all the weird issues that he's facing with numerics.
But even if you use Triton like language, you still need to use some math libraries for transcendental functions.
So language does not solve it. Like you need libraries which need like different algorithms altogether. You're just using an existing language's runtime is not going to help, precisely because of these errors. Okay, so the model of the story is we wanted to build correctly rounded elementary function. So now, till now, it's like the story part, right? Now, the technical part. So what is correctness for a math library? So how many of you have taken a real analysis course? How many have taken a calculus course? So most of you, okay? So how many real numbers? Infinite number of real numbers. It's a collection of rational and irrational numbers. That's how it's taught in your math course, right? There are like lots of them.
Uncountable.
Yeah. So it's not even countable. So this is your real number line. Lots of numbers. And that's what you get when you do computation. Like when you say like limit, or you do like dy by dx, like you can compute a derivative or an integral, you're dealing with real numbers. But you make approximations when you go to a machine, a discrete machine with finite precision. And this V1, V2, V3 are your representable values in your 32-bit representation or whatever, 64-bit representation. Okay? So now you have an elementary function. Elementary functions are functions of a single variable, which involves logarithms, polynomials, and trigonometric functions, and their combination, addition and multiplication of them. So these are called as element, and math libraries provide implementations for them. And the result of an elementary function is an irrational value. What does an irrational value mean? You cannot represent it as p by q. So all numbers that you can represent in any finite precision floating point representation are rational numbers of the form p by q. Okay? So whatever result you are going to get, ln of x, is going to be this irrational value. It's not exactly representable in any representation. You give it more precision, it's not exactly representable, except for some odd cases like 0. Okay? So now what do you need to do? You take the best known algorithm for computing e power x. So if you have taken a basic algebra class like Taylor series, Taylor series with infinite terms and with infinite precision. Okay, it's not achievable in the real world, but let's say hypothetically you do this. And then you do one final rounding. Okay, so there are different ways to round up, round down, round towards 0, or round to nearest. So the most commonly used rounding mode is round to a nearest value around that number. So you do one final rounding, and here V2 is your correctly rounded result. So the model of, or the definition of correctness for a math library: take your best known algorithm, Taylor series, do it with real numbers, compute it, and do one final rounding. Okay. And the holy grail of designing math libraries is to produce this correctly rounded result for every number, for every input. In a 32-bit, there are 2 power 32 such inputs, 4 billion inputs. And in a 64-bit number, there are 2 power 64 inputs.
What about the inaccuracies induced in the while calculating the value itself in the math library?
Yeah, so this is why I said, like, I'm not talking about math libraries, your specification. When you do verification, there is a specification. When you write specifications, you specify with mathematical numbers. So you do your Taylor series approximation with infinite precision and with infinite terms. So I'm not talking about like how you implement it. I'm saying your specification is it's unrealizable. If you did it with real numbers, with infinite terms, and then you did one final round. This is the specification of how do you attain it? That is what an implementation comes in. Okay. So your goal is to produce the correctly rounded result for all inputs. And this is where like your GCC, take any library, it does not produce correctly rounded result. One reason.
You repeat once again what is correctly rounded result.
Okay, so imagine you have sine of x or e power x. The common way to write any such elementary function is a Taylor series. What does the Taylor series say? If you take a function and compute its first derivative, evaluate it over a point, and then divide it by factorial. There is an expansion for it. Okay, for e power x, it will 1 plus x by 1 factorial plus x square by 2 factorial, x cube by 3 factorial, so on. It goes till infinite terms. So there is an expansion for it. It dates back to the old ages, like when the calculus started. So you have this Taylor series. You compute it with infinite number of terms and do it with real numbers, infinite precision. Okay, you computed a result. And then you do one final rounding to the target representation. You're rounding it to 32-bit floating point, right? When you do one final rounding. So this result is the correctly rounded result. You did only one rounding. So the moral of the story is even a correctly rounded result has some error. The whole point is like because correctly rounded result is not exactly representable in the system. So it has some error, but you did only one rounding. Okay. So and you want to produce this result for all inputs. How do you realize the specification?
Result for all.
Oh, sorry.
Same result for all inputs in any context. But
yeah. So you design a library. You have a 32-bit floating point. It has inputs, the 2 power 32 inputs. You need to produce the correctly rounded result for all of these inputs. And when you design a library, you can invoke it in whatever context you want. It should still produce the correct result. Okay. So why weren't like a lot of people have worked on it. Why weren't people producing the correctly rounded result? So the way people did this function approximation, what are you doing? You're approximating all these functions with some polynomials. So you want to compute e power x, you don't know how to compute e power x. So what would you do is you would compute a small function, a polynomial, over a small domain. And this is like 101 of approximation theory in maths. Like even neural networks are function approximations to an extent, right? So they all do polynomial approximation. So people know what polynomials are. A polynomial is of the form like you have some coefficient C0 plus C1x plus C2x squared. C0, C1, C2 are all like coefficients in some representable representation, like double precision, and x and x's are inputs in your representable representation. So you're approximating e power x with this polynomial. Okay. So now what is the goal of this approximation? Get this orange curve as close to the real number curve, that is blue, as much as possible. And such approximations are feasible only over a small domain. And the values are, you're not doing it for like the range of floating point. What is the smallest value that you can represent with a 32-bit float? Is 2 to the power of minus 126 or minus 2 to the power of minus 149. That is the smallest representable subnormal floating point number. And the largest number that you can represent with a 32-bit float is 2 to the power of 128, almost. It's an open interval. You cannot represent 2 to the power of 128 exactly. So the range is very large. In contrast, an integer is, the 64-bit integer is 2 to the power of 63 minus 1 to the minus 2 to the power of 63, right? So it's much smaller. The floating point gives you a much wider range. That's why you use floating point rather than integers, apart from representing fractions. Okay, so you don't want like numbers that large. You want to represent, you want to approximate functions over a very small domain. So to step back, people approximate functions, e power x, elementary functions with other polynomials. Such an approximation works only if it is over a small domain. And to make this entire approximation work, people would approximate the real value. And the idea is called as minimax approximation. You're trying to generate the curve that minimizes the maximum error across all points. You have a function, you're generating another polynomial, it's going to have some error. Your objective function is to minimize the maximum error. This is also called as the L infinity norm. Again, that's just a jargon.
So the analytical expression of the is the blue line.
So e power x, or ln x is your blue line. That is the mathematical function that
generated by, let's say, numerical method like Runka-Kutta.
Yeah. So that is the orange line. Okay. So all those polynomial approximations, like your interpolation techniques or whatever you're going to use, is going to work over a small domain. So this is the first step you need to do, is take this large value, 1 million that you got, and reduce it to a value between 1 to 2. Okay, how can you do this? Like you can express 1 million as 1.3 multiplied by 2 to the power of 20. Okay, you need to do that. Somehow do that translation. Now you got 1.3. Okay, now you do the approximation. And then produce the result using polynomial. And then produce the result for the original input. So you do the first step is to reduce the input from a large domain to a small domain. Do the approximation over the small domain. Get the result. Let's call it y dash. And use y dash to compensate it to produce the result for the original thing. Original input, 1 million that I started out with. So that is called as output compensation. So there are 3 steps: range reduction, polynomial approximation, and then output compensation. These are the 3 main steps in designing an approximation.
But when we do range reduction, aren't we losing precision?
Yeah. So now, how do you do it accurately? You have to do range reduction. You will lose precision. The goal is to do it accurately without losing precision. Okay. And when you do polynomial approximation, you need to do it accurately without approximate as closely as possible. And the goal is to produce correctly rounded result. Okay. So there is range reduction, and then for polynomial approximation, you do the minimax approximation. Minimize the maximum error. All these steps happen in floating point. You pointed out, right? We are going to have some error. Okay. This error has to be so small so that it does not influence the final result. Okay. And this is why people thought this entire problem is very hard. Okay. So, and to concretely say where it actually impacts, let's say this is a number like ln of x. It's very close to the rounding boundary. So v1 and v2 are representable values in your floating point representation. And what is the rounding boundary? Rounding boundary is when if you just go an inch or a centimeter, the decision will change. Right now, this is rounding to v1. If it goes a bit here, it will round to v2. So that is your rounding boundary. A midpoint is a rounding boundary for round to nearest. So this is the freedom that you have with minimax approximation. If when the result is very close to the midpoint, now a small error will make a wrong decision. And now,
when you get when you do range reduction, that
yeah, so when you do range reduction, all those is going to have errors. All those somehow should not influence, should not make you go past this rounding boundary. And the way you do this, you do with larger precision. Like if you're doing a library for 32-bit, you would implement it with like 128 bits so that you don't lose a lot of precision. When you do polynomial approximation, you bound the error so that like you don't, your precision is bounded. And you have to, and this is what, like any small error in this range reduction, polynomial approximation, or output compensation is going to, you're going to mess up with your final result. And if you do this, it rounds to the wrong result. And this was what was happening in GCC and all these libraries. Okay. And it took us like 1 year to understand why this was happening, 1 or 1.5 years, reading about like cool books called Elementary Functions, Handbook of Floating Point Arithmetic, to realize it. And now we are thinking like, and there is also a very deep problem that underlies, right? This problem is called as the Tabor maker's dilemma. William Kahn coined the term. So to produce a correctly rounded result, how much precision do you need to simulate everything so that you get an estimate for it? So this is a much more fundamentally, you cannot like say for this representation, I just need, if I use 128 bits, I will produce the correctly rounded result. Also, it depends on what is how close is the result to the rounding boundary. For some results, it may be very close so that you need like 2000 bits of precision. So deciding it a priori is very hard. And this was the table maker's dilemma that was coined by William Kahn long time ago. And the community of math library developers misconstrued this dilemma as, oh, we cannot build correctly rounded. Like, it's going to be very expensive in terms of performance. And they said like, oh, it's very hard problem. It's going to be very expensive in terms of performance. They just is like, let's do what is good enough. Okay. And that's why we ended up with incorrect libraries. And this is what we wanted to fix. This is where our RLIBM project comes in. Okay. So one alternative way to think about our RLIBM project is, don't think like a mathematician. Think like a computer scientist. Sometimes like I wear both hats. Like I love math. So I'm a computer scientist who's thinking like a mathematician, right? So what did we say? We have 32 bits in our representation. And a lot of great mathematicians and cool people have built techniques where we can identify the oracle. It takes 2 hours to compute the result, but we know what the result for it is. We can't use it in our machine learning training because just computing e power x for one input takes 2 hours. Okay. If you have these oracles, slow oracles, can we build really fast implementation? Okay. So rather than approximating the real value, there was this star that the mathematicians were doing, right? They were approximating the real value and then designing a curve which is very close to the rounding border. What are we saying? Approximate directly the correctly rounded result. Okay. To approximate that, there is a chicken and egg, right? I'm saying approximate the correctly rounded result directly. But you have to know the correctly rounded result. So yeah, you should have an oracle for it. And the oracle is very slow. You can't use it. So we are going to use a slow oracle during the generation process. And then we are going to generate very fast implementation that will produce the correctly rounded result in the library. Okay. So that's the first insight of this work. Directly approximate. We were having discussion. Why don't we just approximate V2? That was the insight that we had. And that led us on a 6-year journey.
Professor, how do you create those oracles?
So there's a great library. That's it's a very deep exercise. But fortunately, the folks in India have built, like, they've spent 30 years of their career building such libraries. It's available. Yeah, there are nice algorithms. Like you do it with variable precision. So you need to identify what are the extremal cases for every function. For e power x, what inputs are very close to the rounding boundary. Okay. And if you know such inputs and you know an estimate of how close they are, you have an error bound about those inputs. Now you need to generate a polynomial whose error bound is less than that. Okay. And then when you do range reduction and various other things, you bound the error. You ensure your range reduction, your output compensation, your polynomial error is less than that. So all the other steps also induce an error less than that. Then you analytically prove this entire implementation is less than that error that will change the decision boundary. So the first step is identifying these extremal cases. So Vincent Lefebvre at INRIA spent that was his PhD thesis, identifying hard to round cases for a lot of elementary functions. So spent very cool work. They use supercomputers in France, ran for about 240 clusters of machines, finding hard to round cases. And 4 years, over a 4-year period, they found it for lots of functions. And that's been a handy resource. And that is what is used in generating these oracles. And then there was a cool result from IBM, Alexander Zev, called the Zev's rounding test. When you get a result, is this result good enough with respect to the? So what you do is you add an epsilon error, and then you see, does it shift past the midpoint or not? If it does, then whatever you did is not precise enough. You need to increase the precision. So there is an onion peeling approach for developing correct rounding. It's again, you need to take multiple courses. I can't do justice in one lecture or 5 minutes. But it's a great question though. How do you design oracles? A couple of great PhDs to be written in that space if you're interested. But coming back.
So you say that it took a lot of compute. So were they taking all of the cases and checking if we can find a case which is very near to the decision boundaries, and that would require running the oracle for a lot of cases.
So they don't do the brute force as such. They do there is a line cutting a segment and identifying how these extremal cases occur. There is a cool algorithm called LLL, Lowash factoring algorithm. So they use that algorithm to find it. It's much more involved. It's even now for me to reconstruct it, it would take hours to actually do this. So it's a very involved algorithm. But just search for MPFR, multi-precision reliably. MPFR on Google. You will get the first link. That is the library. There's a nice a 250-page article on generating oracles for various libraries, the algorithms for them. That would be the starting. Okay, so the moral of the story is, how much time do I have?
It takes an hour and maximum hour and a half.
Oh, so how many more minutes?
Half an hour.
Half an hour? Okay, good. As I said, the goal is to convey ideas, right? I don't have to cover everything. Okay. So what was the key idea in our work? Build on the shoulders of giants. There are a lot of cool seminal researchers have built oracles. Now use these oracles and directly approximate the correctly rounded result. And if I do that, okay, the first idea is to approximate the correctly rounded result and then build fast implementation. Okay, so we separate the problem into 2 parts, divide and conquer, right? That's the mantra to rule. So oracles, people have already done it. So if someone gives you an oracle, how do we generate fast implementations? Okay, so if you do that, when you are building a library for 32-bit float, you implement the library in a 64-bit float. Okay, so V1, V2, V3 are 32-bit values, 32-bit floating point values. Okay, the midpoint of V1 and V2 is not representable in 32-bit float, but it's representable in doubles. Okay, there are a lot more values, about 8 million values that are between V1 and V2 that are representable in doubles. Okay, there is an interval of these values from this midpoint to this midpoint. Okay, so that interval is the freedom that you have. You produce any value in this interval, it will round to V2. Okay, so the first idea was approximate the correctly rounded result. Split the problem into oracle and generating fast implementation. The second idea is there is an interval of values around the correctly rounded result. You produce it, it will round to whatever we want. Okay. Now we want to generate a polynomial. What is generating a polynomial mean? A polynomial is C0, C1x, C2x squared of some degree. What is x? The input that we have for which we want to produce the correctly rounded result. What what is that we don't know? We don't know C0, C1, Cx. Okay? And what do we want? The result of the polynomial has to be, let's call the intervals L and H. L and H. And the result of the polynomial has to be less than or equal to H and greater than or equal to L. This is a linear constraint. And for 4 billion inputs, you have 4 billion linear constraints. Solve them, you have your correctly rounded line. Okay, so just to summarize, what is our algorithm?
How do you decide the degree of the polynomial?
You can do it iteratively. Start with a constant term, 0 degree polynomial. Does it work? You try, it doesn't work, increase the degree. And you keep increasing until you end up with a polynomial that satisfies.
You can also keep increasing to get even more reduced error.
So good enough, right? Like if you produce correctly rounded results for all inputs, what's the point in, like, you're already acing everything, right? You're the best employee in this company. And you can do well and increase more, like your bonuses are not going to be better than anyone else. So you're getting the highest bonus in the company.
Professor, did anybody suggest replacing the polynomial with a machine learning function?
Oh, we have done it. This is where, like, we tried it. We gave it to a neural network, like replace it with a set of functions learned by a neural network. It won't produce correctly rounded result. We gave it to an LLM. We tried all these stuff. Yeah, so it's very hard because the amount of freedom and the boundaries that we are dealing with are very small. And these are not the functions that you see in real life every day, right? That neural networks can approximate. So what are the machine learning algorithms? They are like pattern recognition, pattern recognizers. They should have seen it. Like if you're writing like some Python code and that is very common, right? And there is a pattern that is encoded somewhere in the training set, it will recognize it and give you a prediction. And if you're asking to do something totally different and do it correct, that's where, like, at least we haven't had success.
We estimate C0, C1, C2, or you?
So we use an LP solver to solve for C1, C2, C0, C1, the C2s, various coefficients with 4 billion constraints, and then we get the solution, and then we validate it again.
Where do you explain this? You need X.
X's are the inputs, the floating point inputs that you give. So, like, let's say 1.5, computing ln of 1.5, log f of 1.5, x is 1.5. And the oracle result of log of 1.5 is the result, the correctly rounded result V2. And what does the implementation do? It computes the rounding interval for each of the inputs. You get a linear constraint. Solve such linear programs with billions of constraints, you get the eventual polynomial that you're going to use in your math library.
If that 1.5 now changes to 2.5.
Yeah, so that's why just hold on for 1-2 minutes. Let me go walk over this algorithm, and then I'll answer your question if it's still not clear. Okay, so what do? You have a rounding mode, round to nearest. You have a function e power x that you want to approximate. We are going to use the oracle, generate the compute the correctly rounded result for all of them, because this is the curve or e power x or some function, right? And those all the correctly rounded results are there. Okay. Now, what do? We compute the rounding interval for each of them. So your 1.5 will be here, 2.5 will be here, and so on. Okay. For each input, needs to be, or for each of these inputs, we need to generate a polynomial that gets satisfied. So we're going to generate a polynomial that satisfies a single polynomial. When you give x1, it satisfies L1 and H1. When you give x2, it satisfies L2 and H2. Okay. And this is a system of linear inequalities. You can solve it's ax equal to ax less than or equal to b, right? You solve it, you have your math library. Again, how do you solve a 4 billion linear programming system, right? There were no solvers that would do it. Like we built one. That was my talk in PLDI. Like how do you solve such linear programming solvers? So the moral of the story is, like, I want you to take away a few things, right? What is correct rounding? You do it with compute the function with infinite precision and infinite terms. You do one final rounding to your target representation. That is the definition of correct rounding. Why is correct rounding important? It enables portability. Run your AMD GPU, run it on your NVIDIA GPU. it produces the same result. Right now, it does not. The same code produces totally different results. Okay. Correct rounding addresses it. Now we want to design a function approximator that produces the correctly rounded result for everything. Our idea is to approximate the correctly rounded result directly. And the intuition is there is an interval of real values around the correctly rounded result. It rounds to this value and create a linear programming formulation. Follow a linear program with 4 billion constraints. You got a correctly rounded library. Everyone with me? At least you understood like few things, right? Okay. Okay. So the next step is there are like 5 different rounding modes in the IEEE standard. Okay. So I gave this talk at Google about 4 years ago. One of the suggestions is there are 5 different like you did for round to nearest, which is the most common rounding mode. This is excellent, a great start, but there are 5 modes that can you also, because we love round to 0. Truncation is hardware engineers just love truncation because it makes their life very easy. Round to 0, round to nearest is hard because now you need to identify the midpoint, maintain additional state to identify the midpoint, maintain some sticky bits and rounding bits to identify whether you should round up, round down, and various other things. State is bad when you do design hardware. Okay.
So you have to do the same process for all the 5 rounding modes.
Yeah. So one thing you could do is you could do the same process for every rounding. Okay. But then like that's repeated work, right? You are a library maintainer. Will you maintain 5 different functions for each rounding mode? So one of the suggestions that I got in one of these talks was, can you produce a single polynomial approximation that works for all rounding modes? And Google guys did not care about other rounding modes. They cared more about bfloat16. Can you produce bfloat16 with using a 32-bit library or a 64? Use a double precision library, and it should produce correct result for bfloat16. Okay. So this was the question. Okay, so now you are all engineers, right? You have a math library, a 64-bit math library at your disposal, and your boss comes and tells you, I have designed this crazy representation, but it's just 8 bits. Okay, and produce me a result for this math library. What would you do?
Make that inequality exact and get an overdetermined set of equations.
Oh, you don't have all this, like you're not a researcher, right? Like you are a programmer in a company. Like you have someone gave you a 64-bit library. It's black box. You can do all this stuff. Yeah, sure. But you will have to generate all those stuff. Like it takes time. So like let's say you have someone give you a 32-bit library. Someone give you a 64-bit library. This is what like Intel MKL, math kernel library, or Intel compiler provides you, right? LLVM has libc that provides math libraries. They all provide signf and just sign. The signf is a floating point version of sign, and sign is just the double precision version of sign.
You have to patch zeros and upscale the 8-bit to.
So what you could do, as you are saying, is you could promote a 32-bit value to a 64-bit and call it a 64-bit library, right? So you have a bfloat16 value. It's a 16-bit representation. Promote it to 32-bit. Use the 32-bit library, and then get the result, and then truncate it back to 16 bits. So that would be the naive solution. What would you do? You want to produce a result for a 32-bit function. You have someone gave you a correctly rounded 32-bit library. It needs a 64-bit input. So what would you do? You have an input x in float. You would promote it. Every 32-bit value is representable in 64-bit. So there is no loss of information. And then you get an output in double. Okay. Now what do you want? You don't want a double value. You want a 32-bit value. So you round it to 32 bits. You'll get this result. Okay. This is what any pragmatic developer would do, right? Like if you have one library, you would repurpose it for like what we are doing with LLMs, right? Like you have LLMs, like we repurpose it for all other tasks. But this does not produce correct results. Okay. This is called as double rounding. Okay. So why is there like what was my definition of correct rounding? Do it with infinite terms and one final rounding. Okay. What's happening here? There are 2 roundings happening here. when the math library for 64-bit was developed, there was a rounding done. Okay, so according to this, your 64-bit library is correctly rounded. It's correct. Okay, you got that green dot. But if you look at the 32-bit floating point representations, these are the two representable values. This is like less than the midpoint. So this should round to here, right? But this is at the midpoint, it will round to the wrong value. So there is one rounding here, there is another rounding here. Two roundings, double rounding, and if you do double rounding, you get wrong results. This is why when you write any code that has floating point, you should be very careful. Like any seemingly implicit cast, it's going to. This is why writing an autograd framework, you may think, yeah, it's very easy, right? Like, why does Andrej Karpathy have like 18 hours of lectures writing a micrograd framework? This is because you need to think very carefully about like low-level numerical issues.
While we are rounding it for the second time, we compensate
How will you compensate?
for before.
Yeah, sure, that's a great idea. But like, I would want to see like, what are your thoughts on compensating?
We can scale it up. Last part.
In the library, you
But,
cannot.
why will that be within the error bounds of the function?
Happening inside the library, right? So you cannot.
Yeah, well, you got the result. You can do whatever here, but you don't. This is a black box. You don't want to touch it because you don't have numerical methods expertise, right?
Remember, we can have like, suppose we have we want to work with 16-bit floats and we have a 64-bit math library, so use 4 different floats and like we place them in
Index 5 times, get 5 i's, and then average out.
Yeah, all those are great ideas, but the issue with numerical methods is seemingly great ideas don't work in practice. That's the unfortunate world that we live in, right? Okay, so the moral of the story is double rounding is real issue. Like for example, there are like just search double rounding errors, like you'll get lots of issues. And some of the catastrophes that happen have been because of double rounding issues. Like one of those rovers calculate there was a truncation to 16-bit, like Pathfinder, I think. This resulted in
Missile also.
Patriot missile was slightly different issue, but yeah, there is a rounding issue that is happening, but not double rounding. But at least the Pathfinder was a 16-bit truncation, not representable in the range, causing the issue. So I think I'm running out of time, right?
Still have more than 15, 20. There's no time limit.
Yeah, sure. Like again, like I don't want like it's also good to interact with questions. So what is our magic idea? Like we want double rounding has to happen when you're designing, when you're using a 32-bit library to produce results for 16-bit, 8-bit. You have to do double rounding. What is the next best thing you can do when you have double rounding? Make it harmless. Make it not change the rounding boundary. Okay. So I'm going to tell you the secret sauce. Okay. So let's say you want to generate correctly rounded results for all representations from 1 bit to n bits. Okay. You may have an 8-bit representation, you may have a 16-bit representation, you may have a 32-bit representation. I want to produce correctly rounded results for all inputs in all representations from 1 to 32 bits. Okay. And all rounding modes. 4 or 5 rounding modes in the standard. Our secret sauce is generate a correctly rounded result with our approach for a representation that has 2 additional bits. What is it called? N plus 2 bits. But when we do the correctly rounded result, we produce the correctly rounded result with a non-standard rounding mode called round to odd. What is round to odd? I will give you an analogy, right? So in round to odd, if a value is exactly representable in the representation, it rounds to that value. This is true of anything. 9 is representable in integers, it rounds to 9. Now, if you get a number 9.7, okay, I just have integers. I don't have any fractions. So what would your intuition do? 9.7 is more than half. With round to nearest, you would round to 10. But with round to odd, it rounds to a value that is odd. So in this case, it will round to 9. You get 10.6. It will round to 11. You get 10.1. It will round to 11 because what is the nearest value that is odd? Okay. So this is round to odd. If the value is exactly representable, you represent it with that value. If it's not exactly representable, you round to a nearest value that is odd. So now create a correctly rounded result for a representation with 2 additional bits, n plus 2 bits with a round to odd mode, using the exact method that I described earlier. And when you double round this result to any representation from 1 bit to 32 bits with any of the 5 rounding modes, you produce the correctly rounded result. That's the proof in our POPL 2022 paper. And now this was the result that I presented to Google developers. They were jumping with joy. And now why? Well, again, Google is again, I'm just using Google or NVIDIA or whatever the company that comes to my mind. Like in general, like these are LLVM developers who have been building math libraries in these respective companies, right? Okay, so this is a key idea that we have. Okay, and I'll give you the intuition of why this works. When you want to round any real number to a particular target, there are 3 pieces of information that you need to remember. Okay, what are the 3 pieces of information? Like round to nearest, right? Like let's take the analogy of our restaurant example. You get like 10 rupees 50 cents or 10 rupees 50 paise. Okay, so that's the midpoint. In round to nearest ties to even, it rounds to 10 because it's exactly at the middle. You round to a value that is 10. Why do you do that? Because when you do long summation, you want to eliminate the error. That's why round to nearest ties to even is there. Okay, 10.6, it's greater than the midpoint, it rounds to 11. This is what, like in rounding, you need like 3 pieces of information. One, is the value exactly representable? Okay, so all numbers, all number representation, if the value is exactly representable, you round to that value. There is no information lost. And the second point you need to know is it less than the midpoint or greater than the midpoint? If it is less than the midpoint, with round to nearest, it rounds to the preceding value. If it's greater than the midpoint, it's round to the succeeding value. So you need to know the information, is it less than the midpoint or greater than the midpoint? And the third information, is it exactly at the midpoint? If you want to do decisions for round to nearest ties to even. So you need these 3 pieces of information. If you have these 3 pieces of information from the real value, you can round to any target representation. Okay. So why did we have double rounding errors? Because when you do double rounding, you lost this information. Okay. So now when you do a correctly rounded result with round to odd, you preserve this information. And that is what makes our approach extremely elegant. Okay. So I will save you the trouble of going through the proofs and other things. I have some animation, but I want to say something really interesting. Okay. Okay, so there's an NVIDIA logo on the slide, so NVIDIA guys will be happy, right? Okay, so what did we accomplish by this? We produce a single polynomial that produces correct results for all inputs from all representations from 1 to 32 bits and all rounding modes. Okay, so as a math library, it's a reference library now. It's a fast reference library. You don't have to wait 2 hours with the oracles that you need to get correct results. You have a bfloat 16, you can generate much more faster code for bfloat 16 because it's a small representation, right? You tailor it just for bfloat 16, you can get a much efficient polynomial. But before you even go there, you use a general purpose library, it's good enough for you and produces correct results. You have portability. So I gave this talk again at multiple places. And then one of the questions they suggested is, in your polynomial, everyone is paying the same price. Like a 32-bit float pays the price of a 64-bit float, or a 8B float 16 pays the price of 32-bit float. Can you design polynomials that are faster for B float 16? But I want the entire polynomial to work for 32-bit float as well. And this is one of the joys of giving talks. Right? They ask like a very seemingly innocuous question, but as a researcher, like you have time, like You take these questions and think about it. Like, thanks for all your questions, by the way, because it makes me think. So this was a great question in one of the talks that I got, and then we went back. So what we did is we designed progressive polynomials. What is progressive? You want to produce correct results for all inputs and all representations, use the entire polynomial. You double round it, you get the correct results. And you want it like for B float 16, use the first 3 terms, it produces correct results for B float 16. The same polynomial, first 3 terms. First 4 terms, it produces correct results for tensor float 32. So you want correct results for the entire thing, you get it too. So what do we do with our RLIBM approach? We just change the constraints. So for a particular input, instead of using all the terms, he just uses the first 3 terms, but the same polynomial. And it just magically works. So these are progressive polynomials. So now the last thing I want to say is one of the things. So just to highlight, like your progressive polynomial, you use the entire thing, it produces correct results for B float 16 or the 32-bit float. P1 of x, the first 3 terms produce correct results for B float 16. First 4 terms produce this. I'm just using 3 and 4 colloquially here, but like you can specify it, or the designer can specify it how many ever terms they want.
While specifying that original matrix, how would the constraints be written?
So the constraint should be exactly same. These coefficients should be 0 for that input. Yeah.
So the way we can generate this polynomial for arbitrary floating point representation, like some exponent, some number of exponent bits, some number of matrix bits.
Those are all like, as long as your the actual value is representable in the largest representation that you have, it just works out of the box. Okay. So E4 M3. This is a 8-bit floating point representation that people are excited about, right? Or there is E5 M2. They all work out of the box. Okay. So now what you need to do is you need to solve more constraints, because you just add for a B float 16, you added more constraints. So one of the interesting things that I want to specify is now you have billions of constraints. Okay. How do you solve LP problems with billions of constraints? The success of this entire project hinged on we solving billions of constraints. And we looked at a lot of algorithms. Nothing. You can give this. If you want to really test out LLMs and all your machine learning tools, right? Take a linear program. Take a linear program with 10,000 constraints. Give it to your favorite machine learning tool. It would choke. It would forget about solving it. It won't even produce anything. So I think like machine learning is useful. It uses many of the optimization algorithms that we build in, but it's very far away from solving or even getting close to whatever we want to accomplish.
So aren't there classical algorithms to solve these kind of?
Yeah, there are, but like they're all like they don't handle 4 billion constraints. Each constraint is memory is represented with some k doubles.
Approximate. If they do, they will be an approximate.
No, so what happens is they run out of memory.
So for Google OR tools will take. But
So we use like Google's OR tools, and you give it like they produce answer in reals, and then you round the coefficients back to the floating point. They violate many of the constraints.
it will very clearly says that it does not guarantee optimality.
Yeah, so they solve up to 100,000 constraints, and not billions or millions. Like we tried it with Cplex, Soplex. Name your favorite.
There is one esoteric technique, the icing model, T-Wave user. It's a quantum. They claim it to be a quantum computer. That's probably one place where probably you can.
Yeah, so we tried like again Samir Agarwal at Google. We have been interacting with him in various contexts. So we haven't had luck with like Google OR tools either. So and effectively, like again, our problem is solvable. Even though we have billions of constraints, we don't have billions of variables. The trouble with all these OR tools is they are solving
Metrics. Very sparse metrics.
Yeah, precisely. This is sparse, and also like these are low dimensional. The number of variables are very small. So this is the first observation that we had for solving this. Like, all these linear programs, even simplex, like will not work when you have so many variables. So our idea is like there is a classical algorithm from Journal of the ACM 1995 by Kenneth Clarkson. So which is what we use. So we use randomized algorithms to solve it. Again, I will give you when you design randomized algorithms, the cool thing is designing an algorithm, right? It's very easy. Like just to toss a coin, do something, the algorithm, that's what the algorithm looks like. But proving actually it does the work is the hard part. So what is our algorithm? So we have 4 billion constraints. And what do we need to do? We need to satisfy all of them. And when you have a low dimensional system, each constraint is a vector in a n-dimensional space, right? And if there is a solution for all the constraints, there is a basis vectors, a collection of basis vectors. You identify these basis vectors, you solve the entire system. And if you have k variables, there are k basis vectors. It's kind of a needle in a haystack problem. Now, what are the key constraints that you need to solve so that you solve all of them? Okay, so you can't just choose. One thing you could do if you're naively doing it, right? N choose k. So you know k variables. You can choose. You can compute k. You can choose k constraints out of the sample and then try to iteratively test it out. But n choose k is very large. It's close to n factorial. And when you have n is of the order of billions, you will run out of time. Okay. So what is our algorithm? So the first thing I want you to remember is we are solving a constraint with k variables. So there are k key constraints that we need to identify. So a feasible system, a full rank system is a feasible system. A single solution satisfies all constraints. Okay. So what are we going to do? We are going to sample. And we need to somehow convey the information whether we succeeded in the sample or not. So we are going to do weighted random sampling. What is weighted random sampling? We are going to assign weights to every constraint. Okay, we have to be efficient in memory because there are 4 billion of them. You're already reaching the, like my laptop has 64 GB RAM, or like my servers have 1 terabyte RAM. I don't want to, if I exhaust all of them, like my program won't even complete. So I have to be very careful in utilizing RAM as well. So I'm going to sample 6 k-square constraints. Okay, if I'm looking for a polynomial of degree 10, k is 10. I'm going to sample 6 times 100. Let's say 10 square is 100. So 600 samples, 600 constraints in my sample, right? I choose 6 k-square constraints for my sample. Now I give it to your favorite LP solver, Google's OR tools or Simplex or Soplex, or name your favorite solver. Okay, it'll generate a solution. 600 constraints, everyone can solve it in today's world. If you generate a solution, we are going to check against all the constraints. You got a solution, you check it against all the constraints. The sample is satisfied. That's the whole premise. Now, for any constraint that is violated, we are going to double the weights. Okay, for anything that is violated, the blue bars are the violated constraints, we are going to double their weights. In this case, red. Okay, blue bars are the ones that were sampled. Okay, we test it against everything. Now we throw away the sample. The only information that we are remembering are the weights and the constraint. We sample according to the weights. Initially, the weights were all 1. We uniformly sample 6 k-square constraint.
Weight is a weight in the objective function.
Weight is like just a separate thing that we maintain on the side for every constraint. It's an additional state information that it's not part of the LP system at all.
But it's just a SAT, not a optimization.
It's a weight in your implementation. In your algorithm, you're maintaining some state. Your LP is untouched. Your LP constraints are untouched.
So the next iteration you pick that.
So next iteration, you pick according to the weights. So the probability of picking, when you do weighted random, say you're picking according, the probability is according to the weights, right? Yeah, the probability of picking constraints that were violated in the next iteration is much higher. So you sample again. You get another sample. Now the sample is satisfied. You check against the entire universe. Some of them will be violated. Now double their weights again. What happens is all the key constraints that keep getting violated, their weights will get doubled. And those are the key constraints that need to be picked in your sample. If you solve them, you solve the entire universe. Okay, so that's the intuition. And what we prove in our paper, PLDI 2022, is if you do this for 6k log n iterations, you will get a solution in expectation.
Is that a theoretical upper bound?
Yeah, it's a theoretical limit. But in 100 iterations, we solve like 4 billion constraints. So this is our LP solver. Like it's available publicly for use for anyone who wants to use. And again, it's inspired by Clarkson's algorithm from 1995. And this was key for us to get the math libraries really deployed. Okay, so as a researcher, one of the things you do is when you have, again, I'm telling a story that we accomplished over the 6 years period, right? When we started the RLIBM project, we did not have a LP solver. So how did we make progress? Divide and conquer again. We would split polynomials into small domains and just solve them with existing solvers, and we generated piecewise polynomials. That was our failure to generate a polynomial for the entire thing. So we reported it as a success. And then we kept on working on it. And then once we had this algorithm nailed down, we finally generated a single polynomial without any pieces, with one piece that solves all the constraints. So again, if you're interested, look at my talk. And this algorithm works only when your entire system is feasible with a single solution. And what we realized subsequently is many of the RLIBM constraints are infeasible systems. You give all the 4 billion constraints, no single solution satisfies everything. So what you really want to do is identify a solution. You are generating a math library, right? Which satisfies a maximum number of constraints. And then anything that is not satisfied, you add them as special cases. Okay, so it's called like maxsat. You have a large formula, you want to satisfy a large number of them. Some of those constraints which make it unsat, you remove them. So if you're interested, I have a link to my talk at PLDI on using a beautiful idea from geometric duality to solve it. That's our latest paper from 2024 on it. But to end the talk, I told you a story for a long time, right? Like, oh, math library is what, like, correctly rounded and everything. Does it work in practice? So a single function, you can download it from RLIBM, from our GitHub. It produces, we have 16 functions. It produces correctly rounded results for all inputs and all representations from 1 to 32-bit and all rounding modes. And just to give you an idea, we tested out Intel's glibc, Intel's math library, glibc's math library, and they don't produce correctly rounded results for all inputs and or multiple representations.
Because all constraints can never be met.
They don't even use this approach. They use the real number approximation approach, like they approximate the real value rather than the correctly rounded result. They have a minimax approximation. So that's why they don't produce it.
I have 2 questions. Like first for FP34, how did you decide that you have to go 2 bits more than what is
so
intended?
the proof is the n+1 bit is the rounding bit. It identifies the midpoint. And the n+2 bit is the sticky bit. If you or all bits from n+2 to infinity, that is the sticky bit. So the round to odd maintains the rounding bit and the sticky bit exactly. That is why it's 34. If you look at our proof, that's what we say. So the 34-bit representation with round to odd, it's effectively one is computing the rounding bit, other is computing the sticky bit, and that's why it maintains the information about the real number.
About the RLIBM library, obviously our focus here is more on accuracy than performance. So, like, what are the performance hits if we use RLIBM?
Very good question. Just hold on for a second. Now you said, like, everyone was saying, man, there's no free lunch, right? You're producing correctly rounded results. They should be slower. What we showed, like, Intel math libraries have been optimized for decades. With the help of like 50+ PhDs, like they're like amazing team of researchers. I collaborate with Intel. So take everything I say with a grain of salt. So what is this graph showing? 1.0 is the line where both the libraries are equal. So our speed up over Intel's 32-bit library. So we are faster than Intel's 32-bit library for all functions. And Intel's 32-bit library produces wrong results for almost 100 million inputs. Because 32-bit libraries, it is done with like lower precision approximation, so it's faster, but it produces wrong results all over the place. If you use Intel's double library, it's a bit more accurate. It produces wrong results, but not as bad as 32-bit library. We are almost 2x faster than. Okay, and there is a correctly rounded library for 64-bit called CRLIBM. We are almost like 4 times faster than them, like 3 times faster than them. Okay, so the moral of the story is we are RLIBM is among the fastest math libraries on earth right now.
And is this currently using SIMD or vectorized instructions?
It's using FMAs and vectorization. It does like a string style evaluation, which is easily vectorizable. If you look at the actual x86 or the ARM code that is generated, it's using the vector instructions. Again, we are not doing explicit vectorization with intrinsics. We are relying on the compiler to vectorize, and it handles all those errors efficiently. Okay, so we started this project long ago. 2018 was when we started, and now how many years? Like 6 years hence, LLVM has a math library which is correctly rounded, and this is courtesy of Tu Lee, and we have collaborated with him. We are building a community. So LLVM 32-bit functions, they don't have like correctly rounded for all representations that I talked about, but for 32-bit at least, they have correctly rounded results. So we are collaborating with the community. Like, and you can see, like these are all the LLVM patches. It says like implement correctly rounded results based on the RLIBM library, and we have reviewed these patches and various other things. They're all mainstreamed, and I'm part of the IEEE standards committee. Standards evolve every 10 years. So the 2029 standard discussions are happening right now, and we are making a case that any IEEE 754 compliant machine that is going to be sold, that it's going to say it's IEEE 754 compliant, should provide an implementation of correctly rounded functions. And as you pointed out, C standards also play a role. So explicitly, the next version of the C standard is going to have CR signf, the correctly rounded sign-off versions explicitly in all the C library implementation. So there is consensus building in the community. It's a slow process. Okay, so that said, like to conclude, what do I want to say? The 3 things I want you to remember. 1, if you sometimes dividing your tasks and doing few things efficiently is a good idea. So directly approximate the correctly rounded result. Then you have an interval, solve an LP problem, you have correctly rounded libraries. The moral of the story that I want to, you may forget a lot of things. If you're writing numerical code, be cognizant of the errors. Be cognizant of the things you can make mistakes with. And that will help you go a long way. And then, like I also described to you, one of our favorite results, like just approximate with like 2 additional bits and round to odd. It makes double rounding innocuous. This is extremely useful if you're like an engineer who's trying to do B float 16 or an FP8 arithmetic. So you want to do it with like regular 32-bit instructions on your modern machine. Like you don't want to write a simulator for B float 16, right? So use round to odd. So that makes double rounding innocuous. If you have B float 16 hardware, you don't have to do anything else. Your hardware will do it. But when you're waiting for hardware, you want to write a simulator, like round to odd is a really cool technique to think about. And that said, I want to advertise my students. Like I'm just a messenger here. These are my graduated PhD students, and 2 of them have won the ACM SIG Plan Doctoral Dissertation Award. This is like the best dissertation in the area of programming languages in the entire world for that year. So David Menendez, he did the LLVM verification work. He won it in 2018. And Jay Lim, he did much of the math library work. He won it in 2022. So one of the things I do is I learn from my students. I also program with them, pair program with them. And PhD is a journey where both the student and the advisor grows together. There are a lot of other cool things happening. Some of you mentioned eBPF. Like we have kernel patches to eBPF. Like for example, you talked about tnums. The Linux kernel from 4.14 uses the algorithms that we built, and it's formally verified as well. So we have a paper called Verifying the eBPF Verifier in CAV 2023, which shows the kernel's range analysis to be correct and incorrect. So we are collaborating with the eBPF developers on making the eBPF ecosystem safe. I think like eBPF is a nice way to do telemetry in a lot of containerized settings. So it's a good tool to think about. Like we have some work on cryptography and various other things. If you're interested, look at my webpage and the project webpage. And thanks for all your questions. I know numerics is not an easy thing. It's not as flashy as like I have the next transformers architecture and next cool things I can do with CADs, right? But I hope you learned something from this exercise, and thanks for coming on a Saturday afternoon and listening to a talk on numerics. Any questions?
Yeah, one question. So one thing I want to understand, if somebody gives a new math function now with the exact output, with correctly rounded output, how long does it take to build the polynomial?
So if you have a new function, which is like Bessel function, let's say, or like arctangent, it's a very hard function. So the first thing you need to learn about is how do you do argument reduction, range reduction, because approximating over like a very large domain, 2 to the power of minus 149 to 2 to the power of 128 is very hard. So how do you like do argument reduction? And that is like, this is where you need to read like the old classic books from Cody and Waite and Handbook of Floating Point Arithmetics. Or once you identify these argument reduction techniques, then you can apply exactly the techniques that we have. Use an oracle, generate the correctly rounded result, and then just follow the process. It should be pretty straightforward. If you want to just use our library, you don't have to learn anything. It's just like, yeah, just take it and like just use it. Will work. So there is another, I want to advertise the other project. There is a project from India. Paul Zimmerman has been working on the core math project, which is also making a case. We are co-conspirators in making correctly rounding mandatory for the next versions of the standard. So Paul Zimmerman he's a expert in mathematics, number theory, and numerics. Spent their entire career building numerics. So I think like building on the shoulders of giants, right? Like research does not happen in a vacuum.
I have a question. So if these functions, if we apply some arithmetic operations like multiplication, they further degrade the precision. Is there a way to tackle that? I mean,
that's a fantastic question. So one of the hard things with numerics is errors accumulate. So what I talked about is a single elementary function, right? Now you do like a sigmoid function, which is 1 by 1 plus e power minus x, right? So or some variant of it. So there's error with 1 plus e power minus x. There is error in reciprocal. So you still have to have some error. So what we have built, the community has built some debugging tools, which will tell you is the error large enough to change the to make a difference. But you still have some error, and you have to identify, is this error good enough for you to live with?
So can't the oracle directly approximate or compute?
Then that would be the oracle function that you could do that technically, but that is a new function that you're dealing with. Like given e power x, math library cannot provide every function that you can invariably conceive of, right? So math libraries typically provide about 34 functions that are commonly used. And this is what LLVMs provide, and some complex functions too. But like you can use them to compose. Like you can compute e power x plus divided by k. So now there is some error, half alp error in e power x divided by k. And now if you had computed a function just for e power x by k directly, you would have a different result.
Is currying any significance here? Currying.
Yeah. So you can. What is currying? Like you're partially evaluating. You have multiple inputs. Like you're composing all these functions together. So for the whole point that I was trying to make is floating point arithmetic is not composition. So the errors happen like how you compose, how you compute them. When you compose, the errors are not compositional. So you have to think about additional techniques. Interval arithmetic is one way to reason about it. You can look at dynamic analysis tools where you run the program with measuring error. So one thing that is really useful for the point that you made out is like there is this idea called error-free transformations. So the cool thing about floating point, like there are a lot of bad things about floating points. There is error, non-intuitive, and various other things. But there is an intuitive part. There's a really cool part. Error of a floating point operation can be represented as floating. So when you do A plus B, you're going to have some error with respect to the real result. That error can be represented as a floating point number. So now Donald Knuth, another Turing Award winner, has a cool set of straight line code to compute the error of a floating point operation. It's called two-sum. And then there is a variant of it called fast two-sum, which also computes the error of an addition with just 3 instructions. So you can do these additional things to measure the error. Then say, does it make an impact in your setting?
So there's a question from Microsoft Teams. Manasit, can you go ahead and unmute yourself?
Sure. Hey, so I had 2 questions. Can you hear me?
Yes.
Yeah, we can.
Okay. So the first question is about your solver approach. Do you think this approach, this sampling approach, would work on a SAT or an SMT solver?
So there are 2 ways to interpret the question. One is, can you use a SAT solver to solve this constraint?
No. I mean, can you use this sampling approach to implement a SAT or SMT solver?
I think like you can. It depends on like what your basis set is. Like the whole point about you can implement any randomized algorithm, right? Like our algorithm is very simple. Like just take a sample, evaluate the entire universe, and I cannot give you bounds on whether it will converge and whether it will actually produce a solution. If you want to produce like a best effort to solve SAT problems, like you can try it out. And this algorithm will work when you have this low dimensional LP property that we have.
But it's still not completely solved, right? You still have some constraints that are not solved, that can be solved, which you mention it as special cases, right?
Oh, that is for then, like the whole point is, let's say, what are you doing in SAT? You have a formula. If you know it is satisfiable, and now I want to identify the satisfying instance. Like what is the part that makes the formula satisfiable? You have a very large SAT formula, right? Like maybe billions of constraints, and you want to identify the clause or the subclause that makes the formula actually satisfiable. The rest of it is redundant. You can use our algorithm to find out this instance, the model that makes the formula satisfiable. This is what SAT solvers do. It's an interesting question. I don't know.
Okay, so the second question is about your progressive polynomials. So it seems that is targeted to produce the correctly rounded result for different representations. But my question is from the compiler side. Do you think it might be possible to statically analyze the use of one of your math functions and then choose a representation which maybe is the fastest one if correct rounding is not that required, or maybe the result is not even maybe only some bits of the result for you. So could you switch to could you optimize this representation based on the use of the function?
So that's a good question. So how do you, like, for example, one thing you do and you have a large program, everything is double precision. Now you want to lower the precision so that, like, for some variables, so that you get better performance. You want to use like float wherever possible. So this is called as mixed precision tuning. Like you have a lot of, like, this is a common thing in machine learning, right? Like you want to do training with 32-bit as quickly as possible. Sometimes you have bfloat 16. You want to train with bfloat 16's variable and quantize in other places. How do you replace it? I don't know how math libraries play a role there because, like, for the compiler, the specification that we provide is correctly rounded. Now, if you're using the correctly rounded version of our functions, like it's correctly rounded irrespective of whatever target representation that you're using. It gives it more freedom. Like you have a variable, you think it's favorable. If the compiler decides its heuristics say it's favorable to lower it to bfloat 16, you can use our library still and still be usable. But I don't see explicitly how a static analysis would leverage this information. But that said, like the point that you talk about mixed precision is valid. Like you can use mixed precision, and having a library that provides correctly rounded results with multiple representations. Now, like a compiler has more mileage in like lowering it because it need not be worried now. Like calling an elementary function will make your results look bad.
I think you can think of this as like a compiler IR where you have floating point representations as instructions, and then you propagate this floating point precision on demand, right? When you have more information about the floating point precision, you can just propagate this information and produce a much slower representation. Yeah.
Sure, that's part of mixed precision tuning. I don't see what like math libraries just add on. If you have correct rounding, all it says is irrespective of whatever lowering decision that you did, you're going to be okay.
Sorry. So the part about math libraries in my question was, suppose so you are ultimately evaluating a polynomial. So would it be possible in some cases, provably, to say drop some of the terms of the polynomial and still get a correct result, like depending on the use of the function, for example?
That's a good question, but most compilers don't have this peek into libraries, right? Like typically, like compilers treat library functions as black boxes.
And that's why you can represent libraries as IRs, and then
yeah. So if you now like you have an LTO tool chain where you're doing link time optimization, your library is now compiled as an IR, and you have some summaries which give you additional information, then whatever you're suggesting may be possible. But we haven't explored it. I don't want to overpromise. But that's a good question. So, but this requires your library to be now typically given as in some intermediate representation rather than .o formats. That's the common interchange format for your libraries, right? Or .a. Okay, I'll take a question here.
Yes. So the RLIBM project has a fixed set of functions, and for each function, it has its own custom polynomial that was generated using some generator. Now, let's say that I have a function that is not already in RLIBM. So would it be possible to have a framework where I can define my function, and then the generator that you wrote would generate the polynomials, the coefficients, solve for it, and then give me the correctly rounded version in, let's say, the 32-bit?
We have like open source most of the generator framework. Like everything is open source. The hard part is argument reduction, range reduction, as I said. So that is tailored to the specific function that you're talking about.
Yes.
So if you write your, like, for example, if you want to generate a new function with our approach, all you need to do is take our generator. There are three parts. One is like compute special cases, compute, do range reduction, and do output compensation. You provide, like, plug in those functions, and you know how to play with the rest of the tools. Like, you should be able to generate it.
So I was looking at the source for RLIBM on GitHub, and I see that every function, like within the function body, you have the special cases and range reduction handled. But the generator that you used, is that on a different repo?
So just there is a folder called interval gen.
So this Rutgers APL/RLIBM has include libtest and source. There's no only.
No, go to github.com/ the RLIBM project and then / so they're like go to my web page and then go to the RLIBM project page, and there is a link to the GitHub page. It has an interval gen folder which has all the interval generators. We can take it offline.
You said about the state space. So is it possible to represent in an infinite state space like the Hilbert spaces quantum and then push it through?
I don't have expertise in it. I don't know.
Yeah, so you said that errors usually will accumulate while we are doing multiple floating point operations on a function. So let's say if I have a floating point function which is basically composed of different floating point functions. Let's take a simple case. Let's say tan x cos x. So we know that it evaluates to sin x. So will RLIBM do this internally and take composability into account, or will it calculate for tan x, then separately calculate for cos x, and then multiply it and then accumulate the error?
So RLIBM provides the library provides functions for tan x, and it also provides cos x. So it does not do anything across functions. Like, you will have to do it. So for tan x, we internally compute sin x and cos x, and then we compute the error and make sure the error is half or less for tan x. But like if you do additional things like tan x divided by cos x, there is an error for the division that you need to factor it in as a programmer. Okay. And this is what I said. Like we can't think of like the set of functions that you can write are infinite, right? So we cannot conceive of every function that you can think about and build implementation for it. What we provide is the standard, the floating point standard says what are the functions that need to be provided as elementary functions. There are 34 of them, and we provide implementations for them.
So say like I want to build a complex composite function, which is like I'm doing some math on the functions which you already have. Am I better off making a new framework to, again calculate the constraints and all for this, or am I better off doing error approximation?
So if it's just like, it depends on how many operations that you have. If you have few operations, like all you're doing is tan x by cos x, then doing error-free transformations is a fast. Use the existing functions that you have from RLIBM that are correctly rounded, and then do error-free transformations, compute the error in the division. If you have FMA, you can compute the error in the division with just 2 instructions, and then just use it to approximate the error and then adjust the result. That will be the much fastest way to get the results, rather than building the entire framework all by yourself. Any other question? Yes.
I have a question related to the randomized LP solver. So suppose I have a compiler optimization, which maybe can be boiled down to a combinatorial optimization problem. Can I solve that one faster in using this randomized LP solver?
So that's a good question. So I don't know. Like as I said, like we have 4 billion constraints, but small number of variables. Some of the register allocation instances can be nailed down. Like if you can represent register allocation as a optimization, a linear constraint problem, and then it may have some of the same similarities. Like you have very few registers, 32 registers, right? But the number of constraints that you generate may be in the order of millions. In those cases, you can actually use our randomized LP solver. But the only thing that you have to be cognizant about is there exists a feasible assignment of registers. If it's not feasible, this algorithm will not terminate.
You need to have a solution.
Yeah, a feasible solution. If you don't have a feasible solution, then what happens is your sample, the weights will get doubled up, and the entire sample becomes unsolvable.
Maybe for my case, it may have multiple solutions.
Yeah, so in our case, the system has multiple solutions. Our objective function is true, right? Like we don't have any objective function. As long as you find any objective solution, it's fine. So in our setting, the only requirement is it needs to be feasible. There exists some solution that solves the entire universe. So if you have multiple solutions, it will find something. And next, the question is, if you want a specific objective, how do you factor in the objective into your optimization algorithm? So what you could do technically is, like when you take a sample, you can give in whatever your objective is and maintain the rest of the framework as is. It will just work. Yeah, we have tried it. Like we had a constraint solving problem in a different setting. We had used the same algorithm to make like some interesting choices. So it is it's usable in other settings as well. But the only thing is you need a feasibility solution. If it is not feasible, then you should use our geometric duality idea in our PLDI 2024 paper. That will make it like at least better.
We have a similar problem in case of a polyhedral optimizer, right? Where you have some real optimization problem.
Yeah, so I haven't explored polyhedral constraints from the polyhedral optimization space. That's something we need to explore. Yeah, Pluto generates sometimes like a lot of constraints that are weird to handle. So Pluto is a polyhedral optimizer for people who are not familiar with it. Any other questions? Yes.
What if I build RLIBM with fastmath?
Yeah, we build RLIBM with fastmath. So the whole point is we factor in all the error so that like nothing changes the result.
Okay, so fast math based optimizations or like.
So we factor in all those, like it'll do this FMAs, it'll do associativity, right? In spite of all this, like we use floating point errors as a add-on to the various things. So our code is like error sensitive, and it takes the error in a manner it enhances the final result. So it's aware of the error in the floating point. So this is like one of the key takeaways. Don't get me misconstrued, right? I'm not against fast math. Fast math is needed. Without fast math, there is no vectorization. And the compiler developers are not dumb. Like they're really smart people, like 20,000 of them, and they invest their time primarily because to make your code faster. And fast math is just a hack they have to get performance with the oddities of floating point. And there are other representations that people have been exploring, right? There is a representation called posit. There is a representation called where a precursor to posit called unums. There is now a new representation called tacums, where everything like the goal is to provide like either associativity to some extent, and when does associativity actually matter, the loss of associativity actually matter, and various other things. Okay, any other question?
I think I would just ask what's next. So how do you want to?
Okay, so where are we going next? So there are a lot of like optimization problems, right? Like there is quadratic programming problems. So we are building a new quadratic programming solver using some of the ideas. You can't directly use this idea. So existing ideas that we have. And the other thing is when your application uses different rounding modes, when you call the library, as one of the members in the audience pointed out, we use the floating point error. But when we do the implementation, we use round to nearest. So there is a rounding mode change that we need. So how do we avoid this rounding mode changes altogether? So there are like, again, and there are these domains in robotics where people are doing physics-based simulation. For example, some of you might have seen OpenAI's this video demo, right? Sora. If you look at the video from the OpenAI's demo, it somehow was faking physics. Like if you're physics cognizant, you'd say like there's something odd about the video. The videos are cool, but like that doesn't happen in real life, right? Like it looks like fiction.
Valley type stuff like.
Yeah, so I think to do realistic stuff, like you need to actually have a model for physics. Yeah. And how do you build models for physics? And we have some really cool ideas happening in this space.
I think there's a project from Caltech, right, on the Fourier neural operators.
Yeah, Anima's project, yeah, neural operators. Like, yeah, she's at NVIDIA too. Right?